beam of ABC. So horizontal rigid beam of ABC, 3 meter long. So we have 2 meters here and 1 meter here, 3 meter long. Hinged at A. So the hinged portion is at this point A. Is supported at B. Is supported at B. That is at this point. 2 meters from A. It is supported from 2 meters from A. And by a 2.5 meter long vertical steel rod. So 2.5, 2 plus 0.5, 2.5 meters long vertical steel rod B, D, E is hinged at a ceiling. This is the ceiling what we are talking about. So this is the ceiling. Is hinged at ceiling. The part BD is 0.5 meter long. The part BD is 0.5 meter long and 2000 mm square area of cross section. In the area, while the part DE is 2 meters long and 1250 mm square, 1250 mm square in area. If the beam carries a vertical point load, of 40 kilonewton at the NC, find the maximum stress in the rod. So which is the rod we are talking about? We are talking about this rod, the maximum stress in the rod, and total elongation of the rod we need to find out. So this is the problem which has been given. Now here, so if you want to write the free body diagram of this, so we have it is very similar to a cantilever beam, wherein we have a hinged portion at this. When the load is acting at this point, which is 40 kilonewton. So here what happens is we need to consider the reaction. So what type of reaction we will going to get? Whether we will going to be down or up. So this will going to be 2 meters. So this is A, this is B, and this is C. So this has got 1 meter. Now when the 40 kilonewton is applied here, so in order to keep this body in equilibrium, we have to have a force which is acting in the upward direction. So we will going to consider that point as P. So in order to keep this, so in order to maintain this, so we need to analyze how to solve this problem. So let the maximum, so here the load which is acting at this particular point is P. So then what happens? Considering the moment about the point here, that is 40 into 3 will be equal to P into 2. So that we will be able to find out what is the load coming on this. So that is because we need to find out the maximum stress in the rod. So maximum stress in the rod means what? That will be equal to sigma will be equal to P by A. Here we have two unknowns. One is the stress and the other one is the load, because we don't know what is the load acting on this. So that load what we are considering is P. But we have the load which is acting at this point, which is 40 kilonewton. So now we need to find out what is the load which is acting at this particular point. So once we find out that, we know the P and we know the area of cross section. One is 2000 and this P is say for this entire rod, that is because it is only one load which is acting for the entire cross section. So naturally we will going to have the load will go to the uniform. So once we know this is the area of cross section for this and here this is the area of cross section for this, so then we can find out easily what will going to be the maximum stress in the member. Now to do that, here now maximum stress in the rod first. Maximum stress in the rod. Let the tension in the vertical rod be T. Let the tension in the vertical rod be P. For the equilibrium of the rigid beam, for the equilibrium of the rigid beam, taking the moments about the point A, moments about the hinge A. So here what happens? 40 into 3 will be equal to the sum of the clockwise moment will be equal to the sum of the anti-clockwise moment. So that means which will be equal to 40 into 3 will be equal to P into 2. Therefore, what will going to be the value? P will be equal to 60 kilonewton. 60 kilonewton. Now, once we have the 60 kilonewton, so that means the load acting on this which will going to be in the upper direction. So that means we will going to have the value of P. So now we will going to find out the stresses now. The stress in section BD. Therefore, stress in section BD. So in order to find out the section in BD, so now we will going to consider B and D. So when you have the number here, the B, we have the load which is acting on this direction, which will be 60 kilonewton. Now the rigid bar has got in this direction, which will be like this. So in order to keep this in equilibrium, we will going to have a load which is acting in the opposite direction. So this will go to be the 60 kilonewton. So which will going to be the tensile load. So here it will going to be tensile. So naturally in this section we will going to get this is also 60 kilonewton which is acting in upper direction. So this will be B and this will be D. Similarly on this member we have again the cross section which is of D and E. So again we have a tensile load which is acting at this point which is 60 kilonewton, and again this side will also be equal to 60 kilonewton, wherein we have 1250 mm square is the area of cross section, and the member what we have is 2 meters. Similarly here, so this dB is the length will be 0.5 meters, and this area of cross section is 2000 mm square. So we will go to find out the individual stresses in the member. Stress in section BD will be equal to sigma 1, which will be equal to P by area of cross section of that member. So P is 60 kilonewton. So we will go to get 60 into 10 to the power of 3 divided by 2000 mm square. So that will be equal to 30 Newton per mm square. Similarly, stress in section DE. Stress in section DE. Stress in section DE, which is sigma 2, which will be equal to P by A2. P by A2, which will be 60 into 10 to the power of 3 divided by area of cross section is 1250 mm square. Therefore, sigma 2 will be equal to 48 Newton per mm square. So where you have the maximum stress, which is sigma 2. Therefore, the maximum stress in the member will be sigma 2, wherein you have 48 Newton per mm square. And also we can see from the cross section, where you have the least cross section, there you will going to get the maximum stress. Therefore, maximum stress in the bar sigma max will be equal to, therefore maximum stress in the bar, maximum stress in the bar, sigma max will be equal to 48 Newton per mm square. 48 Newton per mm square, because we have the cross sectional area which is dE. Now we are going to consider the second part of this problem, which is total elongation of the bar. The total elongation of the bar will be delta L. Therefore, the next total elongation of the bar. Total elongation of the bar, which is delta L, will be equal to delta L of AB, delta L of BD and plus delta L of DE. So that will be equal to P into length of BD by area of BD into E plus P into length of DE by area of DE into E. So that will be equal to P by AB will be equal to sigma BD into length of BD by E plus sigma DE into length of DE by E. So sigma BD is nothing but sigma 1 and sigma DE is nothing but sigma 2, that is, which will be equal to, now we can consider 1 by E into sigma BD is nothing but sigma 1 into L1 plus sigma 2 into L2, because sigma BD will be sigma 1 and sigma DE will be equal to sigma 2. So that will be equal to 1 by E. So that will be equal to 1 by 2 into 10 to the power 5 into sigma 1 is 30 into 500, because here we have it in Newton per mm square. The value what we have it is in Newton per mm square, but here it will be 0.5 meters. So you have to convert that into mm. 0.5 into 100 will be equal to 0.5 into 1000 will be equal to 500 plus sigma 2, which is 48 into the length of the member 2 meter, 2000. So that will be equal to delta L, which will be 0.555 mm. So this is going to be the final answer.